We will be presenting InstantMesh, efficient 3D mesh generation from a single image with sparse view large reconstruction models. InstantMesh is a feed-forward framework for rapid 3D mesh generation from a single image featuring state-of-the-art generation quality and significant training scalability using multi-view diffusion model and a sparse view reconstruction model based on the LRM architecture. The problem we face is that although recent advances in machine learning and deep learning have created viable results for 2D image generation, the field of 3D mesh generation has not yet reached the same levels of consistency and efficiency. This paper will have significance in the fields of virtual reality, gaming, industrial design, and animation.
Given an input image, InstantMesh first utilizes a multi-view diffusion model to synthesize novel views at fixed camera poses. These generated images are then fed into a transformer-based sparse view large reconstruction model to reconstruct a high-quality 3D mesh. The whole image to 3D generation process takes only around 10 seconds. By integrating an isosurface extraction module, i.e. FlexiCubes, InstantMesh can render the 3D geometry efficiently and apply geometric supervisions, such as depths and normals, directly onto the mesh representation to enhance the final 3D results.
Moving on to the multi-view diffusion model, in order to prepare the model for fine-tuning training, the authors use 0123++. As input, it takes a query image and 6 randomly sampled target images. It outputs 32 random viewpoints for each object and their corresponding depth and normals maps. LRM demonstrates that a transformer backbone can effectively map image tokens to implicit 3D triplanes with multi-view supervision. This transformer-based approach offers better flexibility and scalability for training, especially on large datasets. For the training, there are 2 stages. In the first, the model is trained using the triplane NeRF representation, building on pre-trained knowledge from OpenLRM and training. In the second, the existing density model is adapted to predict signed distance fields instead of density, and 2 additional MLPs are introduced.
Specifically, the LRM utilizes a pre-trained visual transformer as the image encoder to generate the image features, then learns an image to triplane transformer decoder to project the 2D image features onto the 3D triplane via cross-attention, and models the relations among the spatially structured triplane tokens via self-attention. The output tokens from the decoder are reshaped and unsampled to the final triplane feature maps. Afterwards, the LRM can render the images at an arbitrary view by decoding the triplane feature of each point with an additional shared MLP to get the color and density and performing volume rendering. In the first training stage, the model is trained on the traditional triplane NeRF representation. The NeRF renderer consists of a density MLP and a color MLP. In order to retain high-resolution supervision, the model renders patches which are supervised by cropped ground truth patches. In the second stage of training, the authors switched to the mesh representation for efficient training and applying additional geometric supervisions. They integrate FlexiCubes into the reconstruction model to extract the mesh surface from the triplane implicit fields, as opposed to previous LRM-based methods that output triplanes that require volume rendering. In this training stage, the authors reuse the density MLP from the first training stage to predict the signed distance fields and add 2 additional MLPs to predict the deformation and weights required by FlexiCubes. Since FlexiCubes provides a differentiable shape representation, this enables the model to learn complex geometries and extract a mesh directly from the implicit field. This approach avoids the slow volumetric rendering of NeRF and significantly reduces generation time. Using FlexiCubes allows InstantMesh to use full resolution images and additional geometric information for supervision, such as depth and normal maps, without cropping them into patches. In order to evaluate the success of the paper, the authors split their results into 2 parts, by 2D evaluations and 3D evaluations. The 2D evaluations are pictures of the 3D generated meshes, which are then compared to the ground truth produced by the 3D object datasets. The baselines that the paper compares their results against are produced by related state-of-the-art studies in the field. When comparing the NeRF implementation versus the mesh implementation, NeRF appears to achieve slightly higher fidelity results than mesh. However, FlexiCubes improves the smoothness and reduces the artifacts of the mesh surface due to the additional geometric supervisions, which is seen as generally more desirable. Additionally, for 2D metrics, InstantMesh outperforms the baselines on the SSIM and LPIPS metrics. And for 3D metrics, InstantMesh outperforms the baselines on both CD and FS metrics significantly, indicating a higher fidelity on the generated shapes. Given that InstantMesh outperforms the baseline in 3D metrics, the research presented in this paper presents the most reliable geometries amongst all methods. By using Vejcik cubes, InstantMesh can guarantee smoother results in a faster time frame, as opposed to other standard 3D reconstruction models such as NERV, significantly boosting the training efficiency and reconstruction quality.